In this video we look at the two instructions DAA and TCS. Before we look at how the DAA instruction works. To understand this we first need to look at something known as BCD numbers. As we know, with 4 bits there are 16 possible numbers, i.e. from 0 to 15. You can see the coding here. However, we humans do not use binary numbers but decimal numbers, which are encoded as BCD numbers. You can see the coding here. Not particularly surprising. What is noticeable is that 6 values are not used. We already know how to add 2 binary numbers. We will now look at 3 additions. The well-known binary addition also produces the well-known results. BCD addition should produce these results. Now you could actually develop a circuit that produces these results. The advantage of calculating with BCD numbers would be greater precision with floating point numbers. But a higher memory requirement is necessary. For this reason, and because binary addition is easier to implement, it is better to use it and provide an instruction that carries out the adjustments later if necessary. Let's now look at what this would have to do. The first operation immediately delivers the right result. In the second case you would have to add 6 to the result to get the correct result of 13. In the third case too, adding 6 leads to the correct result of 17. It's easy to see that if the result is greater than 9 you need to make an adjustment. And if this is not the case, then at least when the carry is set. This results in this condition. To translate this into a circuit, let's first look at what bit combinations need to be considered. If the 2 leading bits are 1, the condition is fulfilled in any case. All values are then greater than or equal to 12. Something similar applies to the first 3 bits. If bits 3 and 1 are 1 and bit 2 is 0, then the condition is also fulfilled. This gives us this equation, which we change a little bit and then create this circuit. We test it briefly and find that this idea is correct. We use this result to decide whether we add 6 or not, which means we add 0. We could use an adder here, or even better we use the adder that is already in the ALU anyway. This means our output is set to 0 or 6, which ends up in this final circuit. Now we create another component and use this command. For the calculate method, we translate the circuit shown into Python again. For the fast method we use this simple program line. Subtracting 2 BCD numbers is a bit more complex. To do this, the following equation is calculated for each decimal place. For the example below, this yields these individual equations. The last digit is 3, as it should be. For the second place we get 12. If we were to use the principle of BCD addition, we would get 2 as the result and 1 as the carry. But that's 1 too many. To get the result, we would have to subtract 1. We keep this in mind. For the next equation we get 11, which takes us to 1. Which is right. Now if we were to calculate the next digit just for fun, we would get 10, which takes us to 0. This process could now continue indefinitely. We could now try further examples. In the end you would come to the conclusion that you would always have to subtract an additional 1 if there was no carryover from the previous position. This leads us to this connection when we perform the TCS instruction after the DAA instruction. This results in this circuit. We'll need these in the next video. In the next video we'll look at adjusting the results depending on the instruction executed.